All right, for this video lesson, we're going to be looking at resistance in a circuit. So a few things that you are going to need are a calculator. It doesn't need to be necessarily a graphing calculator, but a scientific one so that it has inverse and functions like that. Small piece of paper, just something to write on. It doesn't need to, you're not going to need to keep this, but just do a little work when I give you the problems to work through, and then something to write with, obviously, with that. A couple things before we get started. So as we start looking at circuits and drawing them in different things, there's just a couple symbols that we're going to need to know. The first one is what a battery, so when we draw them like the schematics of a circuit, we're going to have the battery. It's going to look something like this. It's going to have a negative terminal and a positive terminal, and then typically we'll label the voltage something like 10 volts or whatever it might be. So that's just knowing that's what the battery is and its voltage. A resistor is going to look something like this little zigzaggy shape. It'll typically also have a number written in ohms. So remember, our unit for resistance is ohms. A light bulb is just a specific type of resistor. So they do the same things. They resist the flow of electricity. And it kind of looks like a normal resistor, except it has this little circle around it, which obviously makes it look like a resistor or a light bulb. And again, we'd have another symbol or number that associated with that. Again, I just picked those numbers out of thin air. Every resistor is not 3 ohms. Every light bulb is not 4 ohms. It's just some numbers that I picked out. So from there, we can have these symbols. We can have two kinds of types of circuit arrangements. Now we can combine them so that we have both together, but we're going to look at them separately right now. And the first one we're going to look at is parallel. So parallel means that there are multiple pathways for the current to move through in the circuit. For example, if the battery was, say, somewhere over here and the current gets to this junction here, it can go one of 4 paths. Each individual charge is only going to be able to take one path, but their current is going to move through all 4 of them. So again, parallel doesn't necessarily mean, in this case, they are running side by side. It doesn't mean running side by side. It means I've given the current multiple pathways to move through. And looking at series, there's only one path. So as the current would move around the circuit, it gets to R1, it gets to R2, and it gets to R3. It has to go through all 3 of them. It doesn't have a choice. And we use that toll booth example. So when we did the squishy circuits lab, so here, if this was a road, as I get to this point and I need to pay a toll to use the road, I'm going to either go here, 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 or here. I don't have to go through all 4 of them. I have to go through just one of them. If I set it up like this, I only pay it one, but I'm going to have to travel through each of them because there's only one part of road I can take. That's the big difference between parallel and series circuits. Now, we're going to look at parallel branches first because they're a little trickier to deal with. So we're talking about equivalent resistance. So this REQ, that means equivalent resistance. And what we're saying by that is typically when we have resistors in parallel, they're going to allow the current to move through faster because we're giving it multiple pathways to do that. And so therefore the resistance that these create needs to be smaller. And that's how this equation and this mathematical model is going to work. So again, let's throw some numbers in here. So let's say that R1 is 3 ohms and R2 is 5 ohms. Again, I'm just pulling those numbers up. They could be any different value that we're looking at. So if I go to set that equation up, it would look something like this. So equivalent resistance 1 over 3 plus 1 over 5 all to the negative 1. So if I was going to put that into my calculator here, it would need to look something like this. So the main thing there that we need to do is make sure that you've closed in everything in parentheses, because if you don't put the parentheses and put the negative 1, it's only going to raise that 5 to the negative 1 power, and that's not what we want. We need the whole thing inversed so that I get an equivalent resistance of, we'll call it 1.9, we'll round a little bit, ohms. So what I'm saying with that 1 0.9 is that having two in parallel at 3 and 5 ohms is like having just one resistor in series that's 1.9 ohms. That's all. Now let's say we have 3 resistors in parallel now. So let's assign some values here. Oops, I moved the page a little bit. Let's say this is 2 ohms. Let's say this is 5 ohms. And let's say this is 7 ohms. So again, I'm going to use my mathematical model I had from before. So equivalent resistance is equal to 1 over 2 plus 1 over 5 plus 1 over 7 all to the negative 1, which is going to give me an equivalent resistance of we're going to call it 1.2 ohms. So again, what I'm saying, so just making sure you put that in the calculator correctly when you do that, what I'm saying is, and just to give you a visual this time, these 3 that are in parallel right here would be just like only having one resistor that is 1.2 ohms. So that's the kind of the different what we're talking about. And you notice that 1.2 is less than all 3 of the resistors here, which means we're going to get more current moving through them because we're giving the current multiple pathways. Because really we just have a 1.2 ohm resistor when we have those 3 set up the way that they are. So go ahead and pause the video right now and then go down and answer questions 1 and 2. Now if we look at resistors that are in series, easy thing with them is to get their total resistance or equivalent resistance, we just need to add them up because all of the current is going to have to move through them. So all of the current is going to be affected by those resistors in series. So we're going to have to total it up. So if we look at that, let's say that R1 is 4 ohms, R2 is 6 ohms, and R3 is 3 ohms. So again, just pulling those numbers out. So all I need to do to get total resistance or equivalent is take 4 plus 6 plus 3. I am not going to show this on a calculator because I think you got it. That's going to give me a total resistance of 13 ohms. And you can see the difference between something like this and if those were in parallel, we have a higher resistance, which is going to mean a lower current when we look at those calculations. So then kind of let's say that there's 3 more in series just to make sure we got it. 2 ohms, 3 ohms, and 4 ohms. So again, just to get total, taking 2 plus 3 plus 4, which will be a grand total of 9 ohms. Crazy, right? So 9 ohms would be our total resistance here for just those 3. And again, similar idea with parallel, a lot higher resistance in something in series than compared to parallel. So go ahead and pause the video and answer question 3 and 4. And then make sure you hit submit when you are done. And we're going to pick up with this on Thursday and then talk about some circuits that have both parallel and series components to them and how do we work with those.